What are you trying to take?
IS-120.
Oh, okay.
Yeah, I'm taking it off.
Okay.
And she said,
I'm in a hybrid right now. It's painful.
Is it? That shouldn't be hard.
No.
I'm like,
people don't know how to work an Excel sheet though. It's crazy.
It's like it shouldn't be hard for you.
Here's where I got these numbers. Where'd you get those numbers? 4 times. Every time you do a problem. We gotta go through the, where'd you get the numbers? No, it's with Briggs.
Yeah. What amuses me is that I've been here for 13 years and I've heard the same complaints about people going through accounting class for 13 years. Math majors come back over here and say, yeah, that's...
Weren't you originally an accounting major?
I was. There's a reason why I'm not. Yeah, okay. All right. So let's do some more of these problems with finding critical regions. This is 10.3-3. Let's suppose that x has an exponential distribution.
The TV's not on.
I thought it was. No. I'll wait. There it is. All right. X has an exponential distribution. So we're going to test, we would like to test the hypothesis that theta is equal to 3 versus, now the ones we've done before have been simple hypotheses, but let's see if we can do it as a more general thing. So let's say that theta is greater than 3. Let's say we want to do a one-tailed test where the theta is actually bigger than 3.
Are you recording this?
I am, yes. Would you like me to?
Yes.
Or do you want me to just stop?
No, I didn't see like the one where there's like lines around.
Oh, it's because I didn't have the TV on. Yeah, if I go back over here, there it is.
It's just
Yeah.
okay. I'm gonna this later.
All right. So we want to do this test, and we want to find a best critical region for this. Now notice the one we did last time was just simple simple alternative hypothesis, right? We compared, I think it was mu is equal to one value versus mu is equal to a different value, right? So this case, I want to see, well, what happens if we just leave the theta arbitrary? I can do all possibilities for theta to be bigger than 3, which is typically what we do in a hypothesis test, right? We agree? Okay. So we'll take our random sample. Let's let x1, x2, now to xn be a random sample. Then our likelihood function, we want to our likelihood ratio, we want to calculate the likelihood at 3 versus the likelihood of any other, I'll call it theta hat, just, let's not call it theta hat because we use that for estimators. Let's call it theta naught. The only thing I know about theta naught here is that it's bigger than 3. Okay, because that's my alternative hypothesis, to be bigger than 3, right? Okay, I'm going to fix it for the duration of actually doing these computations, but what we want to notice is that it doesn't matter what value I fix it for, the type of critical region we're going to have is not going to change. That's the whole point of this, okay? So when we write our likelihood function, we're going to take the product of all of the, so that's not going to be theta. We know that theta is 3 in the first case, right? So we'll do the product of the 1 over 3, e to the minus xi over 3, and then we'll have the product of 1 over theta naught, e to the minus xi over theta naught. We want that less than or equal to some constant. We're using the Neiman-Pearson lemma again to figure out what this best critical region has to be. Basically, it's working backward, right? Assume we've got this constant to start with and figure out what the region would have to look like to calculate the probabilities. Okay? That's the idea. All right. So this looks ugly. So let's take the log of both sides. The log of a constant is still going to be a constant. It doesn't flip the inequality. What will happen is that it'll change the products here, of course, to sums, right? So in this first one, this first part here with the 1/3, it'll change the product to a sum, and we're going to be summing up the log of a third n times. So basically that becomes n log 3. And the next piece here, if I think about what the product would do with the exponents, we would add them together, right? So we would have a sum of the x sub i's up in the exponent. And when we do the log of the e, they cancel each other out. So this will give us minus a third the sum of the x sub i's. That's just the top, right? I could think about it the other way around if I really wanted to. If I did the product first, this would be 1/3 to the n. So when you do the log of that, you would have n times log of a third, and then of course I could bring the negative down and make it a log of 3. Everybody see where I'm getting that piece from? Okay, taking the log? Okay. The bottom looks similar, except that the signs will flip because I'm doing minus the bottom, the log of the bottom, right? Because when you take the log of the quotient, you get the difference of the logs. So the signs on the bottom will look similar, but the signs will be the log of the bottom will look similar, the signs will be flipped. So I'm going to get a plus n log theta naught, and then plus this 1 over theta naught sum of the x sub i's. All right. Now again, basically what we're trying to do is come up with a statistic to use, right? We're trying to figure out a critical region. The critical region needs to be based on the sample. Well, the only thing that's based on the sample has to do with anything here is the sum of the x sub i's, right? That's the only thing that's coming out of the sample. So what I want to do is basically solve this inequality for the sum of the x sub i's. Okay. So we do that in this case. This is, and again, all we really care about is if the right-hand side is going to be a constant, right? So I'm not going to rewrite a whole bunch of stuff here. This is a constant, and this is a constant, right? If I move it to the other side, we're still going to have less than or equal to some constant. I'm just going to call it a k. All right, on the right-hand side, we have this 1/3 and this 1 over theta naught. Now remember, going into this, we're assuming that the theta naught is bigger than 3. So if theta naught's bigger than 3, 1 over theta naught is less than 1/3, right? So when I combine these two constants, make this negative a third plus 1 over theta naught times the sum of the x sub i's. Remember, I'm trying to solve for the sum of the x sub i's. When I divide this to the other side, I'm dividing by a negative number because 1/3 is bigger than 1 over theta naught, right? So this becomes sum of the x sub i's is greater than or equal to some constant. I'll call it c. Because again, all we really care about is that it's a constant. Does that make sense? Okay with that? All right. Great. So this is, notice that, again, the whole point of this was I wanted to get to the point where it didn't matter what the theta naught was to find the critical region, which I did, right? Doesn't matter what the theta naught is, I get the same form of the critical region. Now, of course, what the value of that k would be depends on what the theta naught is, right? because this C here, now this C won't matter. Sorry, this C will stay the same no matter what. Okay, but the K will change based on whatever the theta naught is, because I've moved it all over to the other side, right? Okay. So depending on the theta naught, the K will change. Okay. All right. All right, but this is the form of our critical region. The sum of the x sub i's is greater than or equal to C. So what we want to do then is find what this best critical region is. But notice that the best critical region will be the same critical region no matter what theta naught is, as long as it's bigger. Now, if theta naught were smaller, it would flip the inequality would be going the other way, and I can't use the same critical region. Does that make sense? Remember, we flipped the inequality from here to here because this was negative. If theta naught were smaller than 3, if we were trying to do the one-tailed test the other direction, the inequality would go the other way, which makes sense, right? I'm trying to test if theta is bigger than 3, my random sample is probably going to have a sum that's bigger than some value based on the way the exponential function works, the exponential distribution works.
So why do we care about the other criteria?
What do you mean?
So
If I flip the inequality, you mean?
yeah.
Yeah, I'm going to get to that.
Okay.
Yeah, okay. There's a definition that's coming.
Okay.
I'm going to get to that.
That's
Yeah.
just probably really
Right. We
the
didn't.
only
Or
one criteria. But
Yeah.
not the other.
Right. Exactly. Yep. All right. So this is what our critical region, our best critical region is going to have the form. Looks like the C is equal to, or capital C, I guess is what I have here. The capital C will be all of your stuff that's in your random sample, such that the sum of the sample points is greater than or equal to some little c. Now, again, this doesn't matter what the value of the theta naught is, and I'm going to come back to that in a second. But what I want to do now is, for part B, this was part A of the problem. For part B says, if n is 12, find a best critical region if alpha is equal to 0.1. And they give you a hint. Oops, not infinity. I'm doing too many series in that in Calc 2. The hint they give you is actually the theta doesn't matter. They actually write in the book 2 over theta, but since our theta that we're using here is 3 over 2/3. In general, the 2 over theta, sum of the x of i's, is chi squared of 24. It doubles the degree of freedom. Doubles the degrees of freedom. The reason for that is if you have exponential where the theta is 2, I always want to give you a reason of why this is true. If you have exponential where theta is 2, then your 1 over 1 minus 2t would be your moment generating function. This is exponential of 2, right? We agree with that? Okay. I can write that as 2 over 2. That's also this is the same moment generating function for a chi squared of 2. Right? Because remember, for chi squared, it's 1 over 1 minus 2t raised to the r over 2. So this is chi squared. So exponential with theta 2 is also chi squared of 2. And remember, for moment generating functions, if you take independent and identically distributed random variables and add them together, you multiply the moment generating functions together. So if I've got 12 exponentials that have theta equal to 2, when I multiply the moment generating functions together, this is going to change to a 24. because the power would be 12. Yeah. So when you do sums of exponentials where the theta is 2, you get chi-squared in double the degrees of freedom. Double the ones that you add up.
You can use a similar trick for other exponential. I mean, with different theta.
Yeah, absolutely. Yep, you can do a similar. Yeah, because actually the hint they give you in the book actually says 2 over theta. You can do the exact same trick, and it's not hard to see why it's true. Because if you let your y equal 2 over theta x and find the PDF for y, it comes out to be exactly what you want it to be. It'll be 2 over theta e to the minus x over 2.
I think we have to change the variable because we still want 1 minus 2t every single time.
The variable gets changed in the PDF when you do the transformation. If you let the y equals 2 over theta x, then when you do, remember our trick for finding the distribution function? We did this last semester too, but and then move it over to the other side. This is the PDF, or excuse me, the CDF of x, or evaluated at theta over 2 x. Oops, for my y. So then your PDF will be the derivative, which is of course the PDF of x, and then times the derivative, right? So this PDF, of course, is 1 over theta e to the minus x, but I would have theta over 2 y over theta, and then notice and then times theta over 2, and this becomes 1/2 e to the minus y over 2. So you really do get exponential of 2. So it's a nice little trick that happens. I wasn't as worried about that trick, but it's good stuff. It's fun stuff. All right. The important part is that if you have an exponential distribution, doesn't matter what the theta is. If you multiply it by 2 over theta, it becomes exponential with theta equal to 2. But exponential with theta equal to 2 is chi-square on 2 degrees of freedom. And we know what happens when you take chi-squareds and add them together. Sums of chi-squareds is chi-squared, and you add the degrees of freedom. So if you have 12 exponentials with theta equal to 2, you get chi-squared at 24. Okay, that was a lot of words. Why did I care? Okay. Well, if we go to our our chi-squared table, we want a right tail because this was our critical region. This is our best critical region, right? We want a right tail that has a alpha equal to 0.1. So if you go to your chi-squared table and look at chi-squared sub 0.1, chi-squared sub 0.1 on 24 degrees of freedom is 33.2. So your C will be, oops. So this will be your rejection region, such that your sum of your x's is greater than or equal to 33.2. Or, of course, a lot of times you base your critical regions on the mean, the sample mean. So what would I need to do to that inequality to base it on a sample mean? Just divide by 12, right? I hate writing this part here. They like to write a lot of them in terms of the mean. Oops, sorry, wait a minute. It's not quite right. This is this 33.2 isn't quite the right number that I want. Sorry. What do I need to do to this 33.2? How did we get the 33.2? We multiplied by 2/3, right? Right? So I need to undo that 2/3. Remember, we multiply by 2 over theta to make a chi-squared of 24, so I had to undo that, right? So I have to multiply this by 3/2, right? So I'll have to do the same thing here, multiply this by 3/2. Sorry about that. I forgot about the fact that I had to undo the 2/3 that we did. Yeah, and you get, this is equal to 4.15.
So,
I knew the answer was supposed to be 4.15, and I'm doing that in my head. I'm like, that's not close to 4.15. What did I do?
so in our statistical study, we reject every collection of 12 points that whose mean exceed that point.
So if you take a random sample and the mean gets above 4, then you reject the fact that theta was actually 3.
Okay.
And assume that theta is bigger than 3. I don't know what it is, but I'm going to reject and make it bigger than 3. Now notice that it didn't matter what the theta naught was, right? Because remember, when you're doing this critical region, you assume that the null hypothesis is true. That was why I didn't specify what theta naught was. If you actually go through and look at the problem in the book, it says, do this for theta is equal to 5, then do it for theta is equal to 7. Well, you get the same answer, because it didn't matter what the theta that's bigger than 3 is, right? So again, I want to emphasize, note that the C depends on only theta equal to 3, not the theta naught. So we refer to this region, make sure I get the words right that the book uses. So this is a uniformly most powerful critical region of size alpha. Now, it doesn't mean this does not mean that the power is the same no matter what the theta naught is. That's not what it's saying. The power of the test will change as the theta naught changes. Okay? What we mean by uniformly most powerful critical region is that the region gives you the most powerful test that you can, no matter what the theta is. Now, the power might change depending on what the theta is, but if you tried to use a different critical region, the power would be worse. Okay? There's a lot of words in there again. So what this means again is, given a theta naught, this critical region is the most powerful one that you can find, meaning the power is the highest. Okay? What it does not mean is that if I change my theta, the power will stay the same. That's not what that means. What it means is the power will change, but that's also still the highest power you can possibly get. Okay? Now again, the closer your thetas are together, the lower your powers are going to be. So if you've got thetas that are really, really close together, you'll have to increase your sample size to get the power that you want. If there's a certain power you want, really the only way you can control the power is to increase the sample size. Okay? So one of the parts this one asks you to find is... No, it didn't ask you to find that. Sorry. What you might be asked to find, what is the power if theta is equal to 5. So remember, power is the complement of being a type 2 error, right? So this would be the probability that your mean is bigger than or equal to the 4.15 given the theta is equal to 5. What's the probability that you reject when you're supposed to? That's power, right? You agree? So again, to be able to do this, we would have to use the same idea that we did with the chi-squared. So we know that this would be that your sum of your x's, sum of the x of i's would have to be greater than or equal to 4.15 times 12, or 2/5 of the sum of the x of i's would have to be greater than or equal to 4.15 times 12 over 2, and then times, no, sorry, I was right the first time, over 5 and times the 2. Why am I doing that part? Besides being a pain, why am I doing that part? Because now it's chi-squared, right, at 24. Okay. So let's see if I take 4.15 and multiply by 4.15 times 24 and divide it by 5. This gives you 19.92. So this would be, I mean, I could do it with a table, but all the table would tell me is it's between two things. So if I do, let's go back. Get an Excel open. Get a new sheet here. And say we want to do. We're gonna open a typewriter. No. Fine. I'll put the keyboard back on. This is being a pain. All right. So if we do equals, and I want to do the chi-square, I need to do an inverse on the right tail. Or do I, no, I just want to do the chi-squared of the distribution on the right tail, right? And what did I come up with? Shoot. I switched between GeoGebra and Excel too many times. All right, we want 92 with 24 degrees of freedom. And so we get 0.7. This is fairly powerful. Not fantastic, but again, we're only using a sample size of 12. Right? Say you doubled your sample size. Say we took the sample size up to 24 instead of 12. Well, that would take your degrees of freedom up to 48, right? And now you've got a test that's very powerful. No, I can't. I always forget, I'm sorry.
What if you have to times the 4.15 times 24?
Oh, yeah, I would. Thank you. I would need to double this then, too. So that's what, 39.84? All right, so it's a little more powerful. It's still more powerful. Thank you. I do need to double that. Thank you. Because we need to multiply by 12 to start with. Thank you. I forgot to do that part. But it's more powerful than it was. And that was kind of the point. Your power should increase as the sample size increases. Your power should also increase as your thetas get farther apart. Right? If you want to think about it from a different perspective besides exponentials, think about it from normal distributions. If I've got a normal distribution that has whatever mean in the middle, well, we know that another normal distribution is going to overlap it, right? The overlap part's going to be the bad part where you could have errors, correct? We agree? Okay. So there's overlap parts where we could have error issues. Well, what's one way to make these error issues get smaller? Well, this mu goes farther to the right, right? Or I increase the sample size, because what happens to the variance as you increase the sample size? It decreases, right? So if you increase your sample size, then you get things that looks more like this, right? And more like this, and then your intersection's really, really small. Okay? So again, I think you can see it a little bit better from the normal distribution idea, right? But either the parameters get farther apart and your overlap gets small, or you take a higher sample size and your overlap gets small. Now, you can't control where the parameters are. It's kind of the point, right? You're trying to estimate the parameters. You can't control where they are. So if you're going to make something that's more powerful, you're going to have to increase the sample size. Plus, we know when we start making, especially if your statistics are based on the sum of the sample, well, you know that gets closer and closer to a normal distribution by the central limit theorem. So you can definitely control the power by taking higher and higher sample sizes, bigger and bigger sample sizes, by central limit theorem ideas, if you're using a mean or a sum of the random variables. Does that make sense? We okay with that? Let's see if we can do another example like this.
Also, on the so did we consider it was uniform most powerful because it was independent of theta?
It doesn't matter what the theta naught is, it's always going to have the same form.
Okay.
And the reason for that is, of course, that in this particular case, when we moved everything to the other side, and we're doing calculating using the probability of the type 1 error, we assumed the high null hypothesis is true, or it was equal to the value. So now typically you will not get a uniformly most powerful region if you have a two-tailed test, because one part of the region is off to one side and the other part of the region is off to the other side. So if you're finding uniformly most powerful critical regions and getting a uniformly most powerful test, it's typically going to have to be one-tailed. Let's see if we can do another example here. If I can find the problem that I did last night that I wanted to do. What did I do? I just did one of these last night. I think it was a different problem I did last night. All right, let's pick one out of the book. That's easier. I just want to go through another example, make sure that we're all on the same page of how to do these. Because again, they all look alike, right? They're using the likelihood ratio to figure out what the region has to look like. So let's just do one like 10.3-2. We have that x is normal on 0 sigma squared. We want to test the variance is 4 against the variance is 16. And that's what the problem says that we want to do. All right, so we need to remember what our PDF looks like for a normal distribution. Oops, squared in the wrong spot. I put the arbitrary mu in there too, but that's what our PDF looks like for the normal distribution. Okay. So for our purposes, we're assuming that the mean is 0. It really wouldn't matter what the mean is in general, but in this case, we're as long as it was the same for both. Well, we're going to assume the mean is 0 and that the sigma squared changes. So I want to do the likelihood of 4 over the likelihood of 16. So we'll have the product of, well, sigma squared is 4, sigma is 2. So we'll have 1 over 2 root 2 pi e to the minus x squared over 8, and then over the product of 1 over 4 root 2 pi e to the minus x squared over 32. And we want this as less than or equal to k. Notice that the top and the bottom here look a heck of a lot like what we did when we did maximum likelihood estimators, right? And notice our next step is going to be a heck of a lot like what we did for maximum likelihood estimators. We're going to take the log of both sides. Okay? So the log changes the product into a sum. Notice that the 1 over 2 pi's, the 1 over root 2 pi's will cancel each other out, right? The root 2 pi's are going to end up canceling each other out on top and bottom. Now, again, I don't really care what this constant is on the right-hand side. I just want to say that it is some constant. Well, notice that when you do the log, it breaks up this 1/2 and this 1/4 as a constant piece, right? And all we're going to do is just move that to the other side anyway, aren't we? So I might as well just say this is less than or equal to some big constant on the right-hand side and get rid of these things too, right? There's no reason for them to hang around. Okay? When we do the log of this piece, the e, it'll cancel the e, we'll have a sum in the exponent again, right? So we're going to get negative 1/8 the sum of x sub I squared. And on bottom we'll get plus 1/32 the sum of the x sub I squared. Now, which number is bigger? The one. Everybody see where I'm getting that from, by the way, and why I just wrote everything on the other side as a constant? Are we okay with that? Because I don't really care what the constant is. I just want it to be a constant. Okay? All right. All right, so let's look at the left-hand side now. Which number is bigger, the 1/8 or the 1/32? Or the 1/32, right? So when we need to take that constant and move it to the other side, we'll be dividing by a negative. So it'll flip the inequality, right? So we're going to be left with the sum of the x sub I squared is greater than or equal to some constant. Now, I started this problem by saying that your sigma squared was 16, right? But the only reason why the 16 mattered was right here in this part again, right? As long as I picked a variance that was bigger than 4, this fraction is going to be smaller than that fraction, right? Because this 32 came from the variance piece here, didn't it? So as long as we picked a variance that was bigger than 4, this fraction on this sum of the x sub I squareds is going to be bigger than this fraction without the negative sign and this one.
So that's why we can't have the two-tailed test.
That's why we can't have the two-tailed test, right? Because the two-tailed is going to flip the inequality in the other direction. So this will always be greater than or equal to the same constant if we're going to have a critical region of the same size. And it's going to flip the inequality this way. So the critical region that we're going to find here is also going to be uniformly most powerful. Because the value doesn't matter, it's going to flip the inequality the same way and it's going to look exactly the same. So it's going to be uniformly most powerful here. There's nothing special about the 16 except that it was bigger than 4. It's the only special thing about the 16. Okay, that makes sense? All right. So for part B of this problem, it says that if n is 15, we want to basically find the c. Because our critical region now is sum of the squares is bigger than a c, right? We agree? Okay. So I want this to be equal to 0.05. Well, what kind of random variable was x again? Normal, right? When you square a normal, what kind do you get? Chi-squared, right? So to get chi-squared, I have to make sure I divide by the variance, right? So we know that 1 over sigma squared sum of the x of I squareds is chi-squared of n, right? In general. Because if I take the sigma squared inside and pull the squared out, I get x over sigma squared. I get standard normal squared, right? And I don't have to worry about the minus mu here, of course, because the mu is 0. All right, so in our case, it'll be 1/4 the sum from n equals 1 to 15 of chi-squared, or x squared, sorry, of I is chi-squared of 15. So I bump back to the table or grab Excel, one of the two. Chi-squared sub 0.05 on 15 degrees of freedom is 25. Okay. So we would need 1/4 the sum from n equals 1 to 15 to be greater than or equal to, what did I just say, 25? The 1/4 is out in front because I needed the 1/4 to change it to chi-squared of 15. I looked up chi-squared of 15 in the table for 0.05. It was 25, if I read the table right. I did one of these problems the other day, by the way, and worked on it for 20 minutes trying to figure out what I did wrong. I read the wrong column in the table. Literally pulled the wrong number out was why I couldn't get the right answer. 20 minutes. It took me to figure out, oh, hey, I grabbed the wrong number. I was upset and irritated. I might have sworn, but you know, it's possible. Anyway, so then we do the sum of the x squareds here must be greater than or equal to 100. So we found the c value that we needed. Okay. Does that make sense? All right. So from this then, so notice that given the n, we can find the c, right? It's possible that you might want to figure out how big the n needs to get to be able to figure out the alpha that you need based on the distribution. Done problems like that with normal distributions, right? A little harder to do with other distributions, but normal distributions we've done, right? What sample size do you need to make sure this probability is less than this? We've done that with confidence intervals, right? Where you're trying to find the width. Same concept, right? Okay. So this one be a little harder with chi-squared, but with Excel you can probably play around with it and get an idea of how it, if you wanted a certain alpha, you could probably play around and figure out the n and the c to make your power and your alpha to be what you want it to be. We've done that for normal. It's easier to do for normal because we already know how to do things with normal tables. For the other ones, a little bit harder, but with Excel, you could probably do it, right? If you wanted an alpha of 0.05 and a power of, or a beta of 0.1, you could play around with those things, right? Say we wanted to do that, just because. So say that, let's say I asked you to find the n and the c, so that alpha is the probability that your sum of your x of I squareds is greater than or equal to c given sigma squared is 4, and your beta is the probability that your sum of your x of I squareds is less than or equal to c given your sigma squared is 16. We may not be able to do it because it's chi-squareds instead of normals, but at least we can set it up how we know how we could think about doing it. Right? like I said, if you had Excel, you could play with it some because you could change the degrees of freedom on things and just run a bunch of numbers and see what happens. Okay. But let's think about what you would need. So here you would have chi-squared of 4, right? Or sorry, you need to divide by 4 to get chi-squared of n, correct? So your 1/4 the sum of the x of i's squared is chi-squared of n. In case 1, right? You would have to do this up here. And in case 2, your 1/16 sum of the x of I squareds is chi-squared. I think this might be a little bit harder to do for chi-squareds now that I'm thinking about it. Now you could do this for, in this particular problem where we found the n was 15, we already know what the value for c is. It's 100, right? Right? So if we kicked over, in this particular case, if we kicked over to Excel, you could do the probability associated with 100 over 16 on 15 degrees of freedom, right? Because we already know what the C value is. So if you were trying to find an alpha and a beta, so say your alpha, you wanted alpha to be 0.05 and your beta to be 0.1, say, what you could do is kick over to Excel. Let's say we have an n here. Let's just make it 15 to start with. So the way we got the 25 was that we did the chi-squared inverse right tail of 0.05 and the n degrees of freedom over there. So A5. That was where the 25 came from the table. Right? If we notice that the power associated with this, or the beta associated with this would be, it would be chi-square distribution right tail. Our x value would be 100 over 16. The c was 100. We had to divide by 16 because that would be the, I don't want right tail though, I want left tail. It'd be 100 over 16. That's the c value divided by the 16 because our variance was 16 in that case. And it would still be 15 degrees of freedom. Oops. Too few arguments. I want true. Actually, I got a pretty decent beta value already, right? Because our beta would be the probability that the sum of the x squareds is less than the c, given that the variance was actually 16. So I did 100 over 16 to convert it to chi-squared. And looked at the probability that it was less than or equal to that 100 over 16. So I've got a pretty high power to start with. But again, if you wanted to start playing around with changing the power and so forth, well, instead of this 15 here, I would put A5 because that would change your sample size. And then if you wanted to play around with different things, you could figure out the C that you would need and then the other value that you would need as well. So in this case, this was the C. So over here, if you were trying to play around with these things, this would be whatever your B5 value is and multiplied by 4 because that's how we moved it to the other side, right? So if I change this to 20, then you could see, oh, hey, my power got really small, right? But that's how I could play with both at the same time. You fix your alpha at 0.05, and I want a certain power, I can start playing with the ends, and that'll adjust the C, which is then you can see what the power is adjusted there. It's a little bit more tedious, but you can do it with Excel a little bit easier.
So, regardless, we have to assume either the significance level or the C or N.
Yeah, right. Yeah. Well, the C and the N you can play with by assuming the significance level, and then playing around with the other two. Yeah. But besides the normal one, you're not going to be able. I don't think you're going to be able to have a nice system of equations to solve. You'll have to play around with Excel. All right, so we're not going to meet Friday. If you've got questions, I'll be here Friday, but I figured I'd rather just have the time for work for you and ask me individual questions. I'll be around a good chunk of the day Friday and Monday.
I mean, I don't need anything from you for that to add computer science. Right?
You need your supervisor signature for also on that too. Okay.
Donna, do you know talking about that? And they said that there's somebody told Dom it was best to hold on because we don't know if we'll have any computer science. Then you know what they're doing.
Dr. Rockman might do it.
Okay, yeah, it depends on what you're after. If you have budget off on the answer. You can, it doesn't matter if you hold off or do it.
Yeah.
The incoming freshmen are going to have to have classes regardless because we offer it to the incoming freshmen. At some point, we'll have to offer classes. If you're here, a lot of the offer.
Yeah, I talked to Dr. Rock like maybe 2 or 3 times about it, and he said he would do it. So.
We'll figure out something.
Okay. Because I think that I would have to end up taking like maybe like 2 independent studies of the course.
Dom's a year ahead of you two, isn't he?
No.
Is he sophomore? But okay. Julia's planning on graduating next year, though. I think is her issue.
Yeah.
I don't know if he's planning on graduating early or not. But,
no, I don't think so.
Okay.
I need a semester.
That's the issue. If you want to try to graduate early, then we could have issues with trying to get things
yeah,
offered.
no.
Yeah.
Okay.
I'm here.